Okay, picking right back up where I left off, you'll notice a new background. This is my parents' countertop and no longer my coffee table at home. I am home for Thanksgiving just like you. Okay, example 2. A large auto dealership keeps track of sales made during each hour of the day. Let X equal the number of cars sold during the first hour of business on a randomly selected Friday. So Friday, first hour. Based on the previous records, the probability distribution of X is as follows. So they looked at all the previous records of the first hour of Fridays, and they made a probability distribution based on those records, right? So what do we know about the probability distribution? It should add up to 1, and every individual probability should be between 0 and 1. All right, random variable X has a mu sub X of 1.1, so this is my expected value, and a standard deviation of 0.943. Suppose the dealer's manager receives a $500 bonus from the company for every... My parents' dog is being loud, I'm sorry. Shh. All right. From the company for each car sold. So let Y equal the bonus received from car sales during the first hour. So if I let Y equal bonus, I can calculate what Y would be up here, right? So I get $500 for each car. So if I sell 0 cars, I get $0. If I sell 1 car, I get $500. And if I sell 2 cars, I get $1,000. And 3 cars would give me $1,500. All right, go ahead and flip the page over, but you're going to still need to use this chart. All right, so I went ahead. Problem A says sketch a graph of the probability distribution of X and a separate graph of the probability distribution of Y. How do their shapes compare? All right, so I got you started already. Now, I know this is not pretty, but here is my first histogram with the cars, right? So down here I'm going to put number of cars sold. And we know it's number of cars sold during the first hour on a randomly selected Friday. And then here's my relative frequency, another way of saying probability. And I go all the way up to 0.5. I don't need to go all the way up to 1 because my highest probability is 0.4, right? And then over here, I started off and I made the mistake of putting the same X values, but this is actually a graph of Y. So this is bonus dollars. I tried everywhere to find whiteout in my parents' house, and they just don't have it. So you're going to have to live with this ugly sketch. It's one of my few flaws. Cannot draw. All right, so what I want you to do is pause the video and sketch out the histogram for X and Y, and then compare the distributions. Okay, this is what your graph should look like. And oh my gosh, what sorcery is this? They're exactly the same. Did you expect it? I hope you did, because we already talked about it. Remember on the very second page, it said, I'm going to bring it back up for you, shapes of distributions do not change, even if we add or subtract or multiply or divide by a constant, right? And what were we doing here? We were multiplying. We multiplied to get the bonus information, right? We multiplied each of the cars sold by $500. That's all we did. Y is equal to 500 X. That's how we got all the Y values, right? Okay, so now find the mean of Y. You have the tools in your statistical toolbox to do this one of 3 ways, right? You can do it by hand, where you multiply these values down here by the relative frequency and add them up. You could put it in the calculator, where you put these X values in L1, the relative frequencies in L2, and go to one variable statistics, right? Or you can just transform the variables because you already have the mean of X, so you can do the mean of Y. And that's what we're going to do because it takes 2 seconds, right? So the expected value of X is equal to, it told us on the last problem, it was equal to 1.1. So we know the mean is a measure of center. So whenever we multiply or divide the distribution by a constant, we can also do that to the measure of center. Louis, shh. So our expected value of Y is just going to be 1.1 times 500. Remember, I multiplied each of these x values by 500 to get the numbers. I'm going to do the same thing. So my mean of y, my expected value of y, is going to equal 1.1 times 500, which will be 550. All right, calculate and interpret the standard deviation of y. All right, so the standard deviation of y, let me focus this. Let's think about our chart again. When we multiply or divide by a constant, does that change the measures of variability? Let me bring up the chart and we'll see for ourselves. Remember, multiplying or dividing changes pretty much everything except for the distribution. So yes, the measure of variability also changes. So in the problem, it told us our standard deviation was 0.943. So our standard deviation of x was equal to 0.943. So to get the standard deviation of y, which was the probability distribution of bonus dollars, I just take 0.943 and I multiply it by 500. And you get 471.5. All right, from here, what I want you to do is pause the video. I want you to try your own interpretation of this standard deviation right here. And then I want you to go ahead and give D a shot as well. Think about what operation is happening with D and how it affects the measure of center and measure of spread. All right, so don't come back until you do C and D. Okay, so I think I made a slight calculation error with 50 cents. I think it should have been 70 cents, but oh well. All right, so you should have written the bonuses typically vary by $471.70 from the mean of 550. So remember, standard deviation is our typical variation from the mean, right? All right, so looking at part D, the manager spends $75 to provide coffee and donuts to prospective customers. So the manager's net profit, T, so now we have a new random variable, T, during the first hour is 75 less than the bonus earned. So what we're doing here is subtraction. That's how we're transforming y, right? We're subtracting 75 from each number. So describe the shape, center, and variability of the probability distribution of t. All right, well, looking at our previous chart, if we're subtracting, we know our measure of center changes, but our measure of variability and our shape does not. All right, so if we start off by describing the shape's going to remain the same. It'll look just like x and just like y, right? So shape of t will remain the same, which is skewed right. All right, our measure of center does change, so what we're going to do is we're going to subtract $75 from 550. So the mean will be subtracted by $75, so the mu of t, right, this is our new random variable t, is 550 minus 75, which is 475. And then our measure of variability does not change. Standard deviation does not change. So standard deviation of t is equal to 471.70, right? What we calculated in part C. All right, I want you to go ahead and try example 3 on your own. Come back when you're finished. Okay, example 3 is about a baby bathtub, baby safe setting with the temperature. So X is the temperature of the water in Celsius. And Y is the water temperature in Fahrenheit. All right, so here is a quick conversion, right? Fahrenheit equals 9/5 times Celsius plus 32. So we know we've got two operations here. We got multiplication, and we've got addition. So these are our two transformations that are happening with the random variable. So find the mean of y. Well, first we need to know the expected value of x, which they tell us to be 34 degrees Celsius. So the expected value of y, or the mean of y, let's see, with measures of center, it changes with multiplication and addition, right? So if we go back to our chart, if we're multiplying or dividing, it changes our measure of center and our measure of variability. So we're at measures of center here. So we multiply and we add. We do both. It changes both for the measure of center. So what I'm going to do is I'm going to just plug it into the formula. I multiply 34 times 9 over 5, and I add 32 to get my new mean. Oh, where did my calculator go? I found my calculator, and I plugged it into the calculation, and I got 93.2 degrees Fahrenheit. That's my new mean. All right, standard deviation is a little bit different. This is a measure of variability. So when I go back to my chart, I'm going to see that with measures of variability, I don't add or subtract, but I do multiply or divide. So I'm going to take the multiplication part of the formula and use that. So I know that my standard deviation of x is equal to 2 degrees Celsius. So to get my standard deviation of y, I'm just going to do the multiplication piece. 9 over 5 times 2. So I'm going to grab my calculator, and I get 3.6. So my new standard deviation is 3.6. It also says to interpret the standard deviation of y. So we're going to say the temperature of the baby safe bathwater in Fahrenheit, right? Because that's what y is. Typically varies about 3.6 degrees from the mean of 93.2 degrees. Remember, standard deviation is typical variation, right? All right, go ahead and flip the page over. Now, we're all done with transforming, right? We've transformed, we've added, subtracted, multiplied, and divide by the measures of spread and measures of center and the distribution, so we know what that is. Now we're going to start combining. All right, so here is where we actually prove out what happens when we combine. So we're going to keep going with this same employee raise example. So after much thought, Ms. Lucas has decided on a permanent employee wage, and they're randomly assigned using this new probability distribution. All right, so X is my wage, right, my new wage. 9, 12, and 15. Ooh, I'm generous. All right, so probability distribution. 0.3, 0.45, 0.25, they're all between 0 and 1, and they all add up to 1, so it's a valid probability distribution. All right, so I want you to take a second and find the mean and the standard deviation of this in your calculator. Again, you're putting this in L1, this in L2, and going to stat, calc, and making sure L2 is in your frequency. So go ahead and find the mean and the standard deviation, and if you remember what variance is, go ahead and write that down too, but we'll talk about it. In your calculator, you should have gotten an expected value of 11.85 and a standard deviation of 2.22. Now, if you remember the relationship between variance and standard deviation, variance is standard deviation squared. So all I'm going to do is take this 2.22 and multiply it by itself, right? I'm going to square it. And that gives me a variance of 4.93. I'm going to round it to the nearest hundredth. All right, so variance is just standard deviation squared, and remember standard deviation is just the square root of the variance, right? That's the relationship between the two. All right, now I'm also, this was probability distribution X, I'm also every year going to give an hourly raise. The bonuses are assigned according to the probability distribution, so my raise would be $1 or $3. So it's a 70.7 probability I give you $1 raise and a 0.3 probability I give you a $3 raise. All right, so Y is equal to my raise, right? My end of year raise. All right, we're going to do the same thing. Pause the video and in the calculator find the mean, the variance, and the standard deviation. Come back when you're done. Okay, here's what you should have gotten for Y. You should have gotten an expected value of 1.6, a standard deviation of 0.92. I rounded to 2 decimals, and then I squared it to get the variance, okay? So 0.92 times 0.92 gave me 0.85. All right, now let N equal the new hourly wage of the upcoming year, X plus Y. So now we're combining. Oh my gosh, combining. Cannot spell. All right, so This is combination because I'm taking your old hourly wage and I'm adding the raise. So that's why this is called combining. I'm combining your old hourly wage plus your raise to get your new wage, right?